Okay, afternoon, folks. This time around, we are targeting the A-level computer science code 9618, and of interest is the central processing unit architecture. So there are a bit of concepts that we want to discuss together here, such that by the end of this discussion, one should be able to describe the von Neumann architecture, also explain the purpose and role of CPU registers, process components, outputs allow connection of peripherals, the fetch execute cycle, the purpose of interrupts and how they are handled. Also identifying the common causes of interrupts and also categorizing them. We should be able to explain the CPU specification that affects performance. So in this discussion, terms that you might find common the terms von Neumann architecture, CPU, registers, PC, that's program counter, memory address register, MAR, memory data register, MDR, current instruction register, CIR, arithmetic logic unit, ALU, as well as control unit, CU. We will talk about the fetch execute cycle, also interrupts, input output ports. All those things will be discussed in detail. Let's have a look at the core theory behind the von Neumann architecture. Well, in this architecture, we look into input and output devices, also the main memory, which stores instruction data together. Well, we also have the CPU, where we have control unit, arithmetic logic unit, where computations are performed, also registers, we have buses, address bus, data bus, control bus. Now, one important feature to note about the von Neumann architecture is instruction and data, they share the same memory and buses. This leads to a concept that is known as the von Neumann bottleneck. Why do we say bottleneck? Here we are saying there is a competition or competing or for resources. Which resources are we talking about? The bus that is used for data is the one that is also used for programs. So we are going to, with the same thinking and logic, try and see if we can draw solutions to the problems that we have there. The first problem we are interested in von Neumann description. So when we're describing the von Neumann, we are going to be interested in a scenario where program and data are both stored in RAM. So here we can say both program and data are stored in RAM. So this potentially leads to the bottleneck. And accessing of these two is used by the same bus. So we have a common line used to access both. When I say both, I'm referring to program and its data. So whenever we have both program and data occupying RAM and also using the same address buses for movement, then we say that follows the von Neumann architecture. Then next, we're interested in the program counter. See, the purpose of program counter is stores the address of the next instruction to be fetched. So this one stores address of the next instruction to be fetched. So that's the program counter. Well, it increments or changes its state after each fetch. Then something to note, it increments after each fetch. So when the instruction has been fetched, then the program counter does increase its position. The next is memory address register. Well, with memory address register, this it's designed to hold the address of the memory location being accessed. So it holds the address, the address of the memory location being accessed, of the memory location being accessed. Then next we might be interested in MDR, that's memory data register. With this one here, when we talk of memory data register, this temporarily stores data or instruction being transferred to or from memory. So it stores memory or instructions, stores data or instructions, that's memory data register, being transferred to or from memory. Then current instruction register. When we talk of current, it's like what is happening currently. So this stores current instruction being decoded and executed. It stores current instruction being decoded and stored. So that's the current instruction register. It stores the current instruction being decoded and actually in the process of storing it to be executed. So that's the uh, current instruction register. Next is ALU, which is arithmetic logic unit. And here we'll be interested in all computations be logical or arithmetic. They are performed by the arithmetic logic unit. So it uh, performs arithmetic and logic operations within the CPU or central processing unit. So that's where the calculations are done. Then next we're interested in control unit. This one is sends control signals. Sends control signals. That's control unit to do with things such as interrupt. So this one it coordinates to coordinate movement um, as well as execution of instructions, so movement of data and execution of instructions. So all this is done by the control unit. So next we want to look at the fetch execute cycle. When we talk of the fetch execute cycle, here there are steps that are followed where we have fetch instruction, decode instruction, and execute. So we have fetch instruction, uh, we also have decode. So when we fetch, we do decode, and then execute the instruction. Then next is the interrupts. Well, an interrupt, a good example is a keyboard press that generates an interrupt So keyboard press is an example of an interrupt because it sends a signal or it sometimes interrupts so that CPU temporarily pauses execution to handle the input. So keyboard press, it temporarily pause a CPU to pause execution and attend or listen to the input and handle the input. Right. Last is ports, and when we talk of ports, we have got a number of them. We have network ports, USB ports, you name them. So one that's of interest, let's talk of a USB port. This is a connection which helps the CPU to interact with keyboards, USB drives themselves. So one thing to note is USB is a port, not a device. So it's something key to note. I think basically that's it on the first examples we had. So we'll meet again in the second part. We'll discuss more to do with the fetch execute cycle as well as CPU architecture. Thank you.